You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Preference optimization is the family of training methods that guide models to produce outputs humans or AI evaluators find more desirable. Unlike pre-training, which teaches models general language patterns, or supervised fine-tuning, which anchors them with curated examples, preference optimization adjusts behavior based on what people, or their proxies, actually prefer when comparing possible responses. This process is important because usefulness and safety are not only about factual correctness but also about tone, clarity, and appropriateness. For instance, when two possible answers to a question are equally accurate, one may be phrased more helpfully or respectfully. Preference optimization makes models more attuned to these nuances, shifting them from mere predictors of text to assistants shaped by human expectations. In practice, this family of methods includes techniques like RLHF, RLAIF, DPO, and ORPO, each approaching the challenge differently but sharing the goal of aligning models with desirable behaviors. Reinforcement learning with human feedback, or RLHF, is the best-known and most widely used preference optimization method. It combines reinforcement learning, a strategy where models improve through iterative feedback, with rankings provided by human evaluators. Rather than simply showing the model the right answer, RLHF collects multiple possible answers to a prompt and asks human judges to rank them by quality. These rankings create signals that train the model to favor outputs people find more useful, accurate, or safe. The integration of reinforcement learning allows the system to optimize toward these preferences over time, gradually shifting behavior. RLHF represented a turning point in AI development because it bridged the gap between models that were fluent but unreliable and models that could consistently act in ways humans judged as helpful and appropriate. The RLHF pipeline typically unfolds in 3 steps. First, a pre-trained model undergoes supervised fine-tuning with curated examples, providing an initial sense of how to follow instructions. Second, a preference model is trained on human ranking data, learning to assign higher scores to outputs humans prefer. Third, reinforcement learning is applied, using the preference model as a guide to adjust the base model's behavior. This loop of training, ranking, and reinforcement gradually produces an aligned model. The process is resource-intensive, involving large teams of annotators, significant computing resources, and careful orchestration. But the payoff is substantial. Models tuned with RLHF often feel dramatically more usable and safer than their raw or even supervised fine-tuned counterparts, making this pipeline a backbone of modern alignment. The strengths of RLHF are evident in practice. Compared to purely pre-trained models, RLHF-tuned systems provide outputs that are clearer, more relevant, and generally more aligned with human expectations. They are also less likely to generate unsafe or harmful content, since human evaluators explicitly prefer safer answers during training. RLHF makes models more cooperative, responsive, and context-sensitive, which is why it has been adopted across nearly all large-scale AI deployments. The method also offers flexibility. By carefully choosing and weighting preference data, organizations can shape models to reflect their desired brand voice, values, or ethical standards. RLHF has therefore become not just a technical method, but a strategic tool for tailoring AI to specific applications and audiences. At the same time, RLHF has limitations. The process is expensive and labor-intensive, requiring thousands of hours of human evaluation to produce sufficient preference data. It is also vulnerable to evaluator bias, since human judges inevitably bring their own perspectives, assumptions, and cultural norms into the ranking process. These biases can become embedded in the model, creating skewed or inconsistent behaviors. Reinforcement learning itself is difficult to tune and can destabilize training if not carefully managed. These drawbacks make RLHF powerful but imperfect, prompting researchers to look for more efficient or scalable alternatives. In particular, the reliance on human labor has motivated interest in methods that use synthetic or AI-generated feedback to reduce costs and expand data availability. Reinforcement learning from AI feedback, or RAIF, is one such alternative. Instead of relying exclusively on human evaluators, RLAIF uses other AI systems to generate preference data. For example, a smaller or already aligned model might rank outputs for a larger model in training, producing preference signals at scale. This approach dramatically reduces the need for costly human annotation, making preference optimization faster and more affordable. RLAIF can also be applied iteratively, where aligned models bootstrap the next generation, creating a virtuous cycle of self-improvement. While not a replacement for human oversight, RLAIF represents a practical way to expand preference data quickly, enabling alignment work at scales that would be otherwise impossible with human labor alone. The benefits of RAIF are clear. It offers scalability, allowing vast amounts of preference data to be generated quickly. It also reduces dependence on human annotators, who may be limited in number or inconsistent in their judgments. In some cases, RLAIF even improves consistency, since AI-generated rankings can apply criteria more systematically than humans. This makes RLAIF an attractive tool for organizations facing resource constraints. At the same time, it is often combined with smaller amounts of human feedback to maintain grounding in human values. In this hybrid form, RLAIF helps overcome the bottleneck of human labeling while preserving oversight, showing how AI can be used to train AI in a recursive, scalable fashion. Still, RLAIF introduces risks. If the AI systems generating feedback carry biases or flaws, those errors can be amplified when used to train larger models. The danger is that instead of correcting problems, RLAIF could reinforce them, creating feedback loops that entrench undesirable behaviors. For example, if an AI-generated preference dataset consistently favors verbose answers, the trained model may overproduce lengthy, unnecessary responses. Careful monitoring and validation are essential to prevent such distortions. This illustrates the double-edged nature of synthetic feedback. It is powerful for scaling but must be handled cautiously to avoid compounding mistakes. Direct preference optimization, or DPO, takes a different approach. Instead of involving reinforcement learning loops, DPO directly trains models on preference pairs. Given two possible outputs for a prompt, the model is optimized to prefer the one ranked higher. This bypasses the complexity of reinforcement learning and the instability it can introduce. By simplifying the process, DPO makes preference optimization easier to implement, more stable in training, and often faster to converge. It focuses squarely on what matters, teaching the model to recognize and prefer outputs that align with human or curated judgments. DPO has gained attention as a practical alternative to RLHF, offering many of the same benefits without as much overhead. The advantages of DPO are practical and compelling. It is simpler, requiring fewer steps and less engineering than RLHF. It is also more sample efficient, using preference pairs effectively without needing to train a separate preference model or apply reinforcement learning algorithms. This efficiency makes DPO appealing to smaller organizations or those with limited compute resources. It also reduces the risk of instability, since the optimization process is more straightforward. While it may not yet replace RLHF in all scenarios, DPO demonstrates that alignment can be achieved with leaner pipelines, making preference optimization more accessible to a wider range of practitioners. Optimal response preference optimization, or ORPO, is a newer method that seeks to push efficiency further. While RLHF, RLAIF, and DPO each offer advantages, ORPO is designed to combine alignment quality with minimal resource requirements. The method aims to achieve high-quality preference alignment without the heavy costs of reinforcement learning or massive annotation efforts. Though research on ORPO is still emerging, it reflects the broader trend toward methods that make preference optimization easier to scale. ORPO is particularly exciting because it hints at the possibility of alignment methods that deliver strong results even for organizations that lack the massive resources of leading AI labs. When comparing RLHF, RLAIF, DPO, and ORPO, trade-offs become clear. RLHF offers maturity and proven effectiveness, but at high cost and complexity. RLAIF provides scalability, but risks reinforcing model biases if unchecked. DPO delivers simplicity and stability, though it may not yet capture the full subtlety of human preferences. ORPO represents an efficient frontier, promising strong alignment with fewer resources but still requiring validation. The choice of method depends on context. An academic lab may favor DPO for efficiency, while a large corporation may prefer RLHF for reliability, supplemented with RLAIF for scale. These differences highlight that preference optimization is not a one-size-fits-all process, but a toolkit of methods to be applied based on needs and resources. Evaluating preferences is crucial in all these methods. Without clear benchmarks for helpfulness, safety, and factuality, it is difficult to judge whether optimization is successful. Benchmarks test models on their ability to produce coherent, safe, and honest outputs, offering standardized measures of progress. They also reveal where methods fall short, whether in over-restricting creativity, underperforming in safety, or producing factual errors. These evaluations provide the feedback loop necessary for refining preference optimization techniques, ensuring that improvements are not only technical but also meaningful for real-world use. Ultimately, preference optimization is no longer optional. Models that undergo RLHF, RLAIF, DPO, or ORPO form the backbone of nearly all advanced deployments today. From chat assistants to productivity tools, preference-optimized models define the user experience, making systems feel trustworthy, responsive, and aligned with human values. Without these methods, models would remain raw, powerful but unrefined, and unsuitable for widespread adoption. Preference optimization thus represents the crucial middle layer between pre-training and deployment, translating statistical fluency into human-centered reliability. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Data collection is the lifeblood of RLHF, and it is both demanding and meticulous. Human annotators are tasked with reviewing multiple outputs generated by the same model for a given prompt, and then ranking them in order of quality, helpfulness, or safety. This ranking process is deceptively difficult. It requires annotators to carefully judge subtle differences in clarity, tone, factual correctness, and appropriateness. Sometimes two answers are equally informative, but one may be more concise, or more polite, or less likely to mislead. These judgments are subjective and context-dependent, meaning annotators must apply consistent criteria across thousands of examples to produce reliable preference data. The process can involve reading and comparing large volumes of text, highlighting issues like bias or toxicity, and marking when an answer fails outright. This labor-intensive step ensures that the preference model underlying RLHF reflects human expectations, but it also exposes the alignment process to human limitations, such as fatigue, inconsistency, and cultural bias. The sheer scale of human evaluation needed for RLHF creates scalability issues. To train models at the size of modern transformers, tens of thousands of preference judgments may be required, each demanding careful comparison and annotation. This translates into thousands of hours of labor, often spread across large teams of annotators. The cost in time and resources is immense, and only a handful of organizations have the budgets to sustain such efforts. Beyond cost, scalability also introduces risks of uneven quality control. With large, distributed teams, ensuring consistency across annotators is difficult, and disagreements are inevitable. These scalability issues make RLHF an impressive but fragile solution, effective when executed carefully, but prohibitive for smaller groups and difficult to maintain across multiple training cycles. This reality has driven the exploration of synthetic data and alternative optimization methods that can reduce reliance on human labor while preserving alignment quality. Synthetic feedback in RLAIF offers one path forward. Instead of recruiting endless waves of human annotators, organizations can use aligned AI models to generate preference labels for other models. For example, a smaller, safety-tuned model might act as a teacher, ranking outputs for a larger, more powerful student model in training. This bootstrapping process creates a scalable pipeline, AI systems teaching AI systems, multiplying the volume of preference data without multiplying the human workforce. The advantage is clear. A single well-aligned model can generate millions of preference signals at scale, far beyond what humans could realistically provide. These synthetic signals can then be filtered, audited, or occasionally supplemented by human checks, producing a hybrid dataset that combines efficiency with grounding in real-world values. This approach reflects a pragmatic acknowledgement that alignment at frontier scales cannot rely on human feedback alone, and that AI itself must become part of the alignment process. Evaluating preference optimization requires specialized benchmarks designed to test models on qualities beyond raw accuracy. Traditional benchmarks measure factual correctness or narrow task performance, but preference optimization aims at broader goals: helpfulness, coherence, safety, and factual reliability. As such, new benchmark suites include tests for toxicity reduction, bias mitigation, and appropriateness of tone. For example, a benchmark might ask the model to answer sensitive questions and then measure whether the responses avoid harmful stereotypes while still being informative. Another benchmark might test long-form coherence, ensuring the model maintains consistency across extended outputs. These evaluations matter because preference optimization can succeed at improving one dimension, like politeness, while weakening another, like factual precision. Comprehensive benchmarks highlight these trade-offs and provide a structured way to measure whether optimization is actually producing the balanced, human-aligned behavior it promises. Despite its effectiveness, RLHF faces stability challenges during training. Reinforcement learning, at the core of RLHF, can be notoriously unstable. Models may oscillate between behaviors, overfit to specific preferences, or diverge in unexpected ways. This instability means that tuning hyperparameters becomes a delicate art, requiring extensive experimentation and monitoring. For instance, if the preference model is weighted too heavily, the system may generate overly cautious responses that avoid taking risks but feel bland or unhelpful. If weighted too lightly, the model may revert to unsafe or unhelpful behaviors. Balancing this optimization is technically complex, and mistakes can undo weeks of training. Stability challenges remind us that preference optimization is not a plug-and-play solution, but an intricate process requiring careful engineering. They also explain why simpler alternatives like DPO have attracted interest, as they promise to retain the benefits of preference optimization without the fragility of reinforcement learning loops. Direct preference optimization excels in sample efficiency, making it an attractive alternative to RLHF. Instead of building a preference model and running reinforcement learning cycles, DPO directly uses preference pairs to train the model. When given two candidate responses, the model is explicitly optimized to prefer the one ranked higher, without introducing the added complexity of reinforcement learning. This simplicity makes better use of limited preference data, extracting more signal from each comparison. Organizations that cannot afford massive annotation efforts may find DPO particularly appealing, since it allows smaller datasets to still produce meaningful alignment gains. The method's efficiency also makes it easier to experiment with different datasets or alignment goals, since each run is less resource-intensive. In this way, DPO democratizes preference optimization, lowering the barrier to entry and opening the door for smaller research groups and startups to participate in alignment research. Resource considerations weigh heavily on the choice of preference optimization method. Organizations must balance the availability of compute resources, the cost of human labor, and the urgency of deployment. RLHF offers the most mature and tested framework, but requires immense resources to implement effectively. RLAIF reduces the burden on human labor but demands careful oversight of AI-generated feedback to avoid bias amplification. DPO offers efficiency and simplicity, but its capacity to replace RLHF entirely is still debated. ORPO, as an emerging method, promises even leaner resource requirements but remains less proven at scale. Each organization must assess its priorities, whether to invest in robustness and maturity, efficiency and accessibility, or innovation and experimentation. These resource trade-offs explain why the landscape of preference optimization is diverse, with no single method dominating universally. Safety enhancements are one of the clearest benefits of preference optimization. By training models to prefer responses judged as safer or more appropriate, these methods reduce the likelihood of generating toxic, biased, or harmful outputs. This does not mean that harmful content disappears entirely, but the frequency and severity of problematic outputs are significantly reduced. For example, a model trained with preference optimization is far more likely to refuse dangerous requests or to phrase answers to sensitive questions with care. This makes aligned models suitable for deployment in consumer-facing products, enterprise systems, and educational settings. However, safety gains are not perfect, and adversarial prompts or edge cases can still elicit problematic behavior. Preference optimization improves the odds of safe performance but cannot yet guarantee it, which is why additional safeguards such as explicit policy enforcement remain necessary. Transparency concerns arise because users are rarely told which preference optimization methods shaped the model they are using. While experts may discuss RLHF or DPO in research papers, end users often interact with AI systems without knowing whether their outputs reflect human rankings, AI-generated preferences, or other methods. This lack of transparency can undermine trust, especially when users encounter surprising refusals or limitations. For instance, a model might decline to answer a harmless but sensitive-sounding query, leaving the user wondering whether the refusal reflects technical limitations or policy choices. Transparency in alignment methods, even at a high level, is crucial for building trust and accountability. Yet companies are often reluctant to disclose details, fearing competitive disadvantage or misuse of alignment knowledge. This tension between openness and secrecy remains unresolved in the industry. Looking ahead, the future of preference optimization appears to be hybrid. Researchers are increasingly exploring methods that blend human and AI-generated preference data, combining the scalability of synthetic feedback with the grounding of human oversight. This hybrid approach promises to scale alignment more efficiently while preserving sensitivity to human values. Future research may also expand the diversity of feedback, incorporating perspectives from different cultures, professions, and contexts to create models that generalize more fairly. Innovations like constitutional AI, where models are guided by high-level principles rather than individual judgments, may also complement preference optimization. The field is moving quickly, with experimentation across organizations shaping the next generation of methods. Preference optimization is no longer a single pipeline but a growing ecosystem of strategies, each contributing to the collective effort of aligning models with human values. Preference optimization does not operate in isolation. It integrates with explicit policy enforcement to create layered safety systems. Models tuned with RLHF, RLAIF, DPO, or ORPO may still produce problematic outputs, so organizations often add hard-coded rules and moderation filters to catch issues before they reach users. This integration ensures that alignment is both learned and enforced, reducing the risk of failure. Policy enforcement complements preference optimization by covering blind spots and providing fallback protections. For instance, a model might learn to avoid unsafe instructions most of the time, but if it slips, a policy filter can block the output. This layered defense is essential for deploying AI responsibly at scale, demonstrating that alignment is not a single step, but a system of safeguards. Cross-cultural variations complicate preference optimization. What one group of evaluators considers polite, appropriate, or safe may differ dramatically from another group's perspective. For example, humor, formality, and sensitivity around certain topics vary across societies. A model aligned with data from one cultural context may underperform or cause offense in another. This raises profound questions about whose preferences are being optimized and for whom the system is aligned. Addressing these issues requires intentional design, such as collecting feedback from diverse annotators, building region-specific models, or allowing customization for different cultural contexts. Preference optimization is therefore not just a technical challenge, but also a socio-cultural one, where inclusivity and diversity play critical roles in shaping outcomes. Experimentation trends show that researchers and organizations are constantly testing new preference optimization methods. Each method introduces trade-offs, and no single approach fully addresses all alignment needs. Some experiments focus on efficiency, testing lightweight methods like DPO and ORPO. Others focus on scalability, pushing the boundaries of RLAIF. Still others emphasize robustness, refining RLHF pipelines. These experiments reflect the rapid pace of innovation in alignment research, where every advance brings models closer to being safer, more useful, and more widely deployable. The willingness to test, iterate, and adapt ensures that preference optimization will remain a dynamic and evolving field, responding to both technical and societal demands. The implications of preference optimization for general AI development are profound. By making models more aligned with human values, these methods shape not only current applications but also the trajectory toward more general-purpose AI systems. Scalable preference optimization could enable models that adapt flexibly to diverse human needs without requiring constant retraining. It could also determine how power is distributed in the AI ecosystem, whether only a few large organizations can afford alignment, or whether leaner methods democratize participation. Preference optimization thus sits at the crossroads of technical innovation, ethical debate, and strategic competition, influencing the future of AI at every level. In conclusion, preference optimization encompasses a spectrum of methods: RLHF, RLAIF, DPO, and ORPO, each with its own strengths, weaknesses, and trade-offs. RLHF is mature and effective but costly. RLAIF scales feedback but risks amplifying biases. DPO simplifies training and improves efficiency. ORPO promises alignment with minimal resources. Together, these approaches form the backbone of modern alignment pipelines, guiding models to behave in ways humans find more useful, safe, and trustworthy. As the field continues to evolve, hybrid strategies, cultural inclusivity, and transparency will shape the next generation of preference optimization, making it a cornerstone of responsible and practical AI development. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.